Good morning, everyone. Thanks for joining me today as I talk about the MapleSim Battery Library and how system-level modeling can be used to create high-fidelity, efficient models of energy storage systems. So batteries are more powerful than ever, and besides being an important part of our everyday lives, they're also playing a role in storing renewable energy. The recent explosion in electronic devices, electrified vehicles, and smart grid technology has driven demand for rechargeable batteries. Engineers are trying to figure out how to make better batteries, and there's a commercial drive to increase energy density, battery life, improve charge and discharge efficiencies, and enhance thermal stability in order to reduce unit costs and improve product reliability. So in order to support these developments, high-fidelity battery models are required to provide accurate estimates of realistic battery behavior. Battery models allow for the evaluation of battery performance in large systems, and these models also provide access to system-level equations, providing further insight into battery operations. The energy-efficient design of battery-powered systems is becoming increasingly necessary, and battery models have become an indispensable tool in optimizing these systems. With these models, companies are able to understand the loading effect on the battery as it undergoes many different duty cycles and how it will behave as part of the greater system. Battery systems have an impact on product uptime, battery lifespan, heat generation, and product safety, making battery performance a crucial aspect of design. System-level modeling is an extremely effective approach for engineering design projects that can help you reduce development time, uncover problems early in the development cycle, and improve overall designs. By using a system-level modeling tool like MapleSim, battery-powered systems can be modeled far quicker than traditional techniques while still preserving accuracy for meaningful results. With a battery model, you can save time and avoid problems by taking battery behavior into account early in your design process. You're able to understand the loading effect on the battery as it undergoes many different duty cycles and how the battery will behave as part of the greater system. You gain a better understanding of the heat flow in the battery, how rising temperature and age affects efficiency, and what critical factors could cause thermal runaway. You can easily adjust your designs to optimize performance and reduce risks. The multi-physics and parametric nature of MapleSim make it especially well suited to implementing a realistic battery model. The MapleSim Battery Library allows you to incorporate physics-based predictive models of battery cells into your multi-domain system-level models. Using MapleSim, batteries can be modeled and simulated with high accuracy and fast simulation times. The two modeling approaches used in MapleSim are equivalent circuit-based models and electrochemical-based models. Circuit-based models use electrical circuits that reflect the charge capacity and internal resistance through the use of standard electrical components to represent these properties. These equivalent circuit models are conceptually simple, but are capable of capturing many of the non-linear behaviors within the cell. These component models can easily be incorporated into any system model and are generally not computationally expensive. However, their scope of operation is somewhat limited, and it is not easy to map the components of the model to the physical aspects of the real cell. Electrochemical models explicitly represent the chemical processes that take place in the battery. These types of models describe the battery physics in great detail, making the most accurate of all battery models. This physical behavior can be represented by a system of well-documented partial differential equations. However, solving these equations can only be achieved through the use of computationally intensive techniques. This often makes them unsuitable for system-level modeling, since they can take hours to compute the behavior of the battery over just a few seconds. By simplifying the model to a set of ordinary differential equations, MapleSim provides real-time performance while sacrificing very little accuracy of the full physics model. The MapleSim Battery Library includes an extensive list of supported chemistries for modeling lithium-ion, nickel metal hydride, and lead-acid batteries. For the lithium-ion models, there are 14 cathode and 3 anode materials, covering most of the commercially available materials on the market. The graph shows an example of entropy changes for a subset of cathode materials available. We can notice that the different materials have a considerable impact on the entropy change. If we take a look at the battery library components in MapleSim, on the left we can see the electrochemical models available in the battery library, and we can drag and drop them into the model as shown. The battery parameter, including the thermal effects, can be specified on the right. Material selection can be made by selecting cathode and anode material. Similarly, the process is the same for the equivalent circuit model. Here we can see additional battery types to select from, and the approach is much the same, with the parameters specified readily on the right. In this case, the example is showing the anode material selection. The MapleSim modeling approach provides the performance needed for system-level studies with minimal loss in model fidelity. The battery library incorporates voltage profiles, state of charge, thermal behavior, capacity fading, distribution of electrode active materials, distribution of electrical potential, side reactions, and other properties. The ability to model degradation or state of health of rechargeable batteries during operation is critically important for predicting a battery's lifetime. The state of health is determined as a function of battery temperature, applied current, depth of discharge, and cycling time. Modeling thermal effects in batteries is crucial for many applications, such as testing and modeling the battery management system, cooling system control, battery degradation, and energy consumption. The user can allow for energy loss through heat. This makes these models useful for performing thermal studies to determine component sizes in cooling systems, allowing for management of battery temperature. Not carefully controlling this temperature can lead to reduced operational life or, in extreme cases, destruction or even explosion due to thermal runaway. A common problem in many battery-powered systems. There are 3 options for the thermal model: isothermal, convection cooling, and external heat port. The external heat port allows other thermal components to be connected with the cell to simulate heat transfer between the cell and other parts of the system, such as heat transfer between the cells within a battery pack. The MapleSim Battery Library includes a template for estimating battery parameters based on experimental data. Using the global optimization techniques, the worksheet can effectively search for multiple parameters and find the best possible solution. MapleSim provides a system-level understanding of battery behavior, ensuring better, safer performance, and can be used in any modeling project that involves batteries, including electric and hybrid electric vehicles, power electronics, energy generation and storage, consumer electronics, and more. Typical MapleSim battery library uses include battery load analysis and optimization to maximize time between charges, hardware-in-the-loop testing, thermal modeling and cooling system optimization to stabilize battery temperature, the study of mechanical loading effects on battery charge, state of health effects on charge-discharge efficiency and thermal runaway, and battery aging and degradation studies. As manufacturers face the challenges of delivering products that are economically attractive while fulfilling their environmental and legal demands placed on them, complex mathematical models of the products are becoming increasingly important and increasingly complex. The flexibility of component-based modeling within allows the development of highly accurate and customizable battery models. These new battery models can then be incorporated into larger system models, allowing the development of the complete system by integrating the various subsystems into one environment. These subsystems can come from various engineering domains, such as mechanical, electrical, chemical, thermal, and so forth. It uses a schematic approach to defining the model. You simply connect components together and the environment takes care of the math for you. Once a model has been created, the system equations and parameters are available for analysis and optimization, allowing you to not only ensure that the system will work, but enabling higher performance while reducing development costs. MapleSoft Engineering Solutions provide advanced system-level modeling and simulation tools and services that enable innovation and reduce development risk. System-level modeling is an extremely effective approach for engineering design projects that can help you reduce development time, uncover problems early in the development cycle, and improve overall designs. At MapleSoft, we've got customized training courses and contract staff, along with a full suite of services that we can customize to your system-level modeling and simulation needs.